Hello students, welcome back. Previously we completed up to section 2. Now let's go to section 3. This time we are going to consider the geometric property of real numbers, or more precisely, the completeness property. The set of all real numbers completely fills up the number line. In part 2 we went through the order property, and before that arithmetic properties. Through those we saw that the set of all real numbers is linearly ordered, so we can arrange all the real numbers along a line. Yes, we could do the same thing to integers or rational numbers too. They all fit on a line. But for real numbers, the real numbers completely fill up the number line. No gap. So there's one-to-one correspondence between every point on a line to a real number, and that allows us to consider the coordinate system, Cartesian coordinate system. So any point on a plane can be considered as pair of real numbers, x comma y, right distance and upward distance. And as you can see, here are some examples. Yeah, the very same example I use for intermediate algebra and elementary algebra. Quadrants, coordinate axis, you know all those, right? And then if you're on higher dimension, just take triple and quadruple, quintuple, and so on to get R3, R4, R5, and so on. How about R1? Yeah, that works too. We have a number line, but we cannot see R1 very well. We can see R2 and R3. R4 we can't. And R3, well, we can see, but it's difficult for me to draw. So let's focus on R2 for the time being. Yeah, we're going to talk about higher level geometry, higher dimensional geometry later in the second half of the course. But let's have a brief preview of what's to come basically. And they're all coming from this. Line corresponds to real numbers, and the real numbers have all the arithmetic and ordering property. So a lot of geometrical properties can be translated into some arithmetic or some algebraic properties so that we can apply some algebra to answer geometry questions. Here's some example. Points. A point is a member of the Euclidean space. In general, n-dimensional space, but usually two space so that we can see. And then the distance formula, we can use Pythagorean. It's easy to follow, right? And the midpoint formula, yeah, it's easy to follow. And then internal section point. Yeah, the point that divides a number line in a ratio of m to n. In this particular case, 3 to 5. Let's run it again. 4 to 2, 2 to 1, etc. And then you can even consider external section as well. Yeah, here's a line. Line segment P1 to P2, but external section P to P1, P to P2 is 1 to 3, but I don't know. Yeah, we have a formula there, but I don't really see any importance of it. Anyway, we can do all those through some arithmetics. So instead of describing all those in English sentences and then doing all those, descriptive geometry, we can convert all kind of things to algebraic expressions and run those in computers. How about lines? Okay, these are lines. We can define a line as a set of points that are placed in the same direction. What do you mean by direction? It's coming from the vectors. Oops. So basically we can define kind of like this, P0 plus TV, and that'll apply in arbitrary dimension. In case of two dimension, then each vector has only two components, x and y, so we end up with equation of x and y only. And then in the vector equation, we didn't see anything other than linear combination. Yeah, just linear combination, t times v, nothing more than that. Just addition and scalar multiplication by just t. So we don't have any nonlinear term there, just first degree terms only. So that's general form, and then 1-point form, 2-point form, normal line equation, parallel line equation. I want some pictures. Did I prepare some pictures? Symmetric equation, intercept equation. Did I prepare some pictures? Okay, alright. These are more elementary pictures, alright. Slope intercept form, slope point form, 2-point form, alright. And the horizontal line and vertical line. As for these, yeah, we're going to come back and discuss these in the second half of the course. Some more pictures. Okay, alright. Conic sections. Yes, we'll study some conic sections. So we have cones like this, circular cones like this, and then cut those based upon some planes. Depending upon the angle, we get various different types of curves. Parabola, circle, ellipse, hyperbola, like that. And then example of a circle. Definition is a set of all points that has the same distance from the center. General form. Okay, alright, we have a picture. Yeah, okay, standard form, and so on. So what do we get? We get all those nice pictures of circles, and before those lines, and now ellipses based upon algebraic equations. And in order to answer questions about these geometrical figures, all you have to do is to do some really tedious computation with those algebraic equations. And before computers, those were kind of, extremely tedious jobs. But nowadays, it's a matter of programming. And here's some examples of hyperbola. And examples of parabola. All these are coming from some algebraic expressions of x and y, and that's because there's a one-to-one correspondence between the set of all real numbers and all the points on a line. Of course, if you just take Cartesian product of two lines, then we have entire plane, and that allows us to consider all those two-dimensional geometry here. I don't think I prepared any 3D geometry here in this notebook, but we'll do those kind of things in the second half of the course. Let's see, do we have some more? Some parametric curves? Okay, alright, we can define a curve by a function, a pair of functions, x of t and y of t. X is horizontal distance, y is vertical distance from the origin. And then x and y have to be continuous. Otherwise, we're going to get some gaps and some jumps. And here's an example of a line. Yeah, okay, alright. here's a direction and starting point, set of all points that points to the same direction from the starting point. Let's see. I think I may even tried. Okay, I prepared an animation. Let's see how's that look like. Okay, this red vector, red arrow, points toward the position vector of the point, but the direction vector is actually this blue. So starting point is not from the origin where the observer is, but starting point of the motion, that P0, then this direction of motion is actually parallel to this direction vector V. How about this? Okay, we have some ellipse. A cosine of t, b sine of t, and apply Pythagorean identity. Let's see. This way we get a parametric curve as a trace of moving dot. Look at the tip of this red arrow, which represents the position vector for given time. We can do all those because of the geometrical property. The real number arithmetic basically is the key to answer all kind of questions on geometry basically. Here's a little bit more interesting picture. X and y are given by these trig functions, and a lot of sines and cosines, and they're all periodic. So no surprise we have a periodic curve like this, closed curve. And then here is a visualization. Trace of moving dot generating a curve. One more. Okay, we'll have time for one more. Slow down a little bit. I just named it butterfly for an obvious reason. And then again, you can retrieve this purple curve by taking a trace of moving dot, and the parameter here is t, and that represents time. So we can define all kind of curves and visualize all kind of curves through some algebraic expressions or parametric functions, and that's all coming from this property actually. And we can combine this property and apply those to Euclid postulates and answer some questions on Euclidean geometry and study some further examples. But these are going to be the topics that we will consider in the second half of the course. So let's postpone those. And we have enough time, so let me just leave these open so that you can read these. Yeah, we can answer all these kind of questions through just algebraic computations, through arithmetics. For example, there's one and only one line that runs through a pair of distinct points. You can actually prove that through some arithmetics. A pair of distinct lines must intersect at a unique point or at no point. We can prove all those kind of things. We'll do those in the second half of the course.